aqui. Pronto, acho que, professor, quando o senhor quiser começar, viu?
Okay. Very good morning, everybody. The speaker of today is my friend Philippe Robutel. We are colleagues from the same lab in different epochs, in different times. He will speak about a very interesting and very hot subject, which are the resonant planets of the discovered by the mission TESS. It's a new space telescope that has been launched some 2 or 3 years ago to catch new exoplanets. And I am honored to be here, the chairman today, and I invite Philippe to start his talk.
Thank you.
I will ask everybody to set off micros and cameras to avoid to allow a better quality in the transmission.
Okay, so thank you, Silvio, and good morning. So, as Silvio said, I will talk about a very interesting planetary system, which is a TOI 178. So, oh no, the pointer. You see the pointer here? Yeah, thank you. Okay. So, first, as Silvio said, the TESS is a mission, a special mission designed to monitor 500,000 of nearby stars and to focus on Earth and super-Earth sized planets. The telescope here monitors the brightness of stars, and then when a planet crosses the disk of the star, it generates a typical, it generates a typical dimming in the light curve. So you can think that there is something interesting here, a planet, for example. So in August, no, not yet. 2018, TESS observed the planet, the star TOI 178. It's about 12 magnitude star in the constellation of the Sculptor, so you can see it from the south hemisphere. The star is smaller than the Sun, and its radius, its mass and its radius are smaller. So okay. So that's the light curve. So TESS observed during 27 days the star, the light of the star, and then here you can see some dimming at some time of the light, and then here the TESS reduction pipeline has assigned these events to planetary transits. So more precisely to 3 planets. The first one here, this structure there, corresponds to 4 transits of the same planet, a planet of period about 6.55 days. And then here you have 3 transits of a second planet of a period, orbital period, of course, of about 10 days, and the last 2 transits here corresponds to another planet with a period of less than 10 days. Okay. So this here you have the what you can get from TESS. So you you have the periods of the planets here and the radius of the planets. You assume that the orbits are circular because with 2, 3, or 4 transits, you cannot measure the eccentricity of the planet. So we assume that it is circular. We will see that it's the case. So you see that the radius the radius of the planet are not very constrained, especially this one. Okay. But here, if we consider these 2 planets, the planet 1 and the planet 2 with 3 transits or 2 transits, you can see that the ratio of the orbital period are very close to 1. So we can suppose that these planets are in mean-motion resonances, but more precisely the 1-to-1, so the co-orbital resonance. With knowing the time, the instant of the transit of the planets, we can compute the difference of mean longitude of the 2 planets, and then it's in this interval. So here, with this data here and there, we can see that the system is close to equilateral triangle. Okay. And so something like maybe a Lagrange configuration. And you have a 3rd planet for transit. This is an inner planet here. And you can see also that this planet is close to the 3-to-2 mean motion resonance with the 2 potential co-orbitals. So these systems makes a good candidate to harbor co-orbital planets. We can see if we'll see. Okay, so in the solar system, of course, we know a lot of co-orbital bodies. The Jovian Trojan that you can see here in front of the L4 and L5 Lagrange point here of Jupiter and Sun here, with a small libration around this point, small to moderate, a few dozen of degrees. You have also the well-known satellites of Saturn, Janus and Epimetheus, with a very large amplitude of libration in rotating frame. The orbits are horseshoe-shaped. And then you have some of the co-orbital bodies with different kind of trajectory, like quasi-satellites, or so on. Okay. In the model of formation of planetary formations suggests that co-orbital exoplanet exists, but to date nothing like that has been detected. There is several reasons for that. So first, maybe it does not exist, but I don't think so. But the problem, one of the problems, is that the detection of co-orbital exoplanets is very challenging. So first, you have here the best case, the ideal case, if the 2 planets, the 2 co-orbital transits the star. Okay, so you can measure the radius of these 2 planets and the angular distance between the 2 bodies, and then okay, it's very easy in this case, and we thought it was the case for TOI 178. It's not. More difficult if you have only 1 planet. You see the transit of only 1 planet. It's possible, for example, when one of the planet is too small to generate observable dimming in the light curve. It's another case is if you have mutual inclination, a few degrees is enough. So this planet here transits and this one not. So in this case, if you have additional information, you can do something. two cases. This one, you have transit of a planet and you have TTV, so variation of transit time. If the motion of the planet is Keplerian, the time span between successive transits is constant. If there is something else, perturbation due to other planets, the time between two transits varies. So here you have this on this example. You have the red curve that corresponds to the mid-transit time. Okay, but the problem is, so if it's due to perturbation of planets, generally in resonance, in mid-motion resonance, to solve this problem, to know what is the other planets, the problem is completely degenerated, and you can find a lot of solutions. So, okay, it could be due also to a distant moon that orbits the planet. And you have another case here. You have the transit of the planet, and you monitor the radial velocity of the star. It's the reflex motion. Well, no. So in this case, it's much more simple. If the orbits of the two planets, the two co-orbitals are circular, you can, here you have the center of mass of the two planets here, and when the center of mass of the planet crosses the line of sight, the velocity of the mass center, which is also collinear to the velocity of the star, is perpendicular to the line of sight. So the radial velocity is equal to 0, of course. So you are here in this case, but if you look at the brightness of the star, it's of course constant because nothing transits at this moment. Then after, the planet here transit, and then you have this dimming and the life curve. And between these two events, you have a delay. And this delay, you can indicate the presence of orbital planets. This delay can be linked to the orbital period of the two planets, to the difference of the mean longitude of these two planets on something related to the masses of the planets. Okay, so it's very simple in the circular case. When the planets are not circular, that's much more difficult. And here you have a reference when we develop a method to get rid of this problem. Okay, so, and two transit, one transit only, and two no transit. But of course, you have the radial velocity of the star. So in this case, you have, say, two cases. The first one, the two planets are very close to triangular configuration. The libration, the deformation of the configuration is very small. And then you cannot make the difference, looking only at the radial velocity of the star, you cannot make the difference between the two planets in co-orbital motion and a single planet. So it's impossible. You have another solution, completely different. It's the case when the amplitude of libration of the motion here, for example, if it's in the case of horseshoe orbit, is very large. So in this case, the velocity, you have modulation of the radial velocity. You have an example here. It's a theoretical example. That's the radial velocity of the star. The short period corresponds to the orbital period of the planets, and the long period, the modulation here is equal to the libration period of the planet. So the relative motion between the two planets. So, and then you can deduce, if you are able to measure the amplitude of the modulation on the frequency of the modulation, you can deduce that you have a co-orbital motion and obtain some information about the planets, about the mass, the planetary masses. Okay, but if you want to do this, it's possible only in few very special cases. You must have very large libration, co-orbital libration. The two planets must have comparable masses, and you need to have a lot of data. So it's not something that you see every day. Okay. So let's go back to our system. So we have these three planets and maybe two planets. These one are in co-orbital motion. So just a few words about co-orbital dynamics. So here we start with very usual things, the elliptic elements, semi-major axis, eccentricity. I assume that the motion is planar. The mean longitude and the longitude of the very centers. We can use a canonical variable, for example, Poincaré variable here. When lambda, capital lambda is associated to the mean motion and the x are proportional, more or less proportional to the eccentricity vector. The Hamiltonian, you can split the Hamiltonian of course in two parts, the Keplerian part and the perturbation that correspond to the interaction between the planets. Of course, this perturbation is small with respect to the Keplerian part for the epsilon. Epsilon is here the sum of the planetary masses divided by the mass of the star. And then you have also an integral, the angular momentum. Okay, so to go further to describe the motion, first we start by defining two values of the action here, for which the mean motion, the Keplerian mean motion, are the same. Of course, you know, we are in co-orbital motion, so the mean motion are very close one to another. Once you have this quantity, this lambda, that gives you semi-major axis also, and of course, these two semi-major axes are practically the same. Okay, so now you will average your problem, your Hamiltonian. You can define zeta 1, which is the difference of the mean longitude. You take another coordinate, which is one of the mean longitude of the planets, the conjugated transformation. Here we work in a neighborhood of this value, so these two semi-major axes, and then of course this angle, this one, the difference of the longitude, very slowly with respect to this one, with respect to the orbital period. So you can average your Hamiltonian on a given domain here, and then you can transform your Hamiltonian, your initial Hamiltonian, in its average part plus a remainder. So the average, of course, it's here. And then you have Z2 with this change of coordinate is the angular momentum. So if you expand the Hamiltonian in terms of eccentricity or Poincaré variable, that's equivalent, you get something like that. And what is important is that due to the invariance of this integral, the angular momentum, which correspond to the invariance of the problem by rotation, and then this monomial that appear in the expansion are always even. So as it is even, it's obvious to see that the manifold that correspond to circular motion in the average problem is invariant by the flow of the average Hamiltonian. So in the case of the eccentricity, T's are small, that's what we assume, we can study the dynamics of the problem, co-orbital problem, on this manifold. So the Hamiltonian on this manifold read is something like that. So of course it's an integrable problem because you have one angle, it's conjugated variable on an integral here. So here you have the two semi-major axes, but these two semi-major axes, of course, depends on the two variables Z1 and Z2, and then you also Z2 is the constant of the problem. So the phase portrait. So with this coordinate here, you have the difference of the mean longitude, and here's the variable Z1, which is associated to the semi-major axis of the co-orbital. Of course, if you are here on that line here, Z1 is equal to 0, so the two semi-major axes are equal. And for example, if you start trajectory start in this region, so the planet 1 in this case is the outermost, and then it's evolve, and here the two semi-major axes are equal, and then the two planets reverse their role, and the planet 1 is now the innermost. And then, so of course, here you recognize these two fixed points that correspond to the triangular, to the equilateral Lagrange configuration, and then you have in the blue region libration around these two, so deformation of this equilateral triangle that in the solar system correspond to the place where are the Trojan, the Jovian Trojan here. And then you have here a separatrix that corresponds here, this fixing point correspond to the Euler configuration where the two planets are in both sides of the star here. Of course, you have this region with very large amplitude of libration that, for example, correspond to the case of Janus and Epimetheus. On here, in the gray region, you are no more in co-orbital resonance. So, just a point about the size of this region, the region, the width of the tadpole region, this one, is of order square root of epsilon, while the horseshoe region is of size cube root of epsilon. And just a remark here, of course, or maybe here, you have a point here and there that's the same, that corresponds to collision. And then you have this region, which is the collision region here of this size. And then the average Hamiltonian, of course, if you are in this region, the remainder is smallest than the perturbation, but here it's not the case. So the average the average Hamiltonian is not valid, of course, in this region, but it is there. Okay. So here it's numerical simulation of the problem, our problem with the two planets, only two planets for the moment, and the star here. So the initial conditions are chosen like that. So here you start with the difference of the mean longitude equal to this quantity. The eccentricity, the initial eccentricities are equal to 0. And then you have two quantities here that varies. That is the initial ratio of the the orbital period of the planet, which corresponds to some power of the ratio of the semi-major axis, of course, the initial semi-major axis. And then, as we don't really know what are the value of the planetary masses, here you have the epsilon in this axis. So here, if you are far, not very far, too far, but if you are not too close to 1 here for the ratio of the semi-major axis of the orbital period, we are outside of the co-orbital resonance here. So you have quite stable motion with in gray on white, it's unstable. So here you have gap that corresponds to mean motion resonances, of course. And when the ratio of the semi-major axis or the orbital period tends to 1, mean motion resonances accumulates in this region and generate a huge unstable region. And then here you are in the co-orbital region. Of course, when the planetary masses increase, the co-orbital region increase. It's what I said here in the previous slide here, because the size of this region is about epsilon 1 to the third, or so. If you have taken initial condition here in this unstable region, you are out of the co-orbital resonance. Then if you increase the mass, of course, the size of the resonance will increase, and then you fall in the horseshoe region. And then if you have a point here, you shoot something there, it's the same thing, and you fall here in the blue region that correspond to libration around L4 on L5, the equilateral equilibrium. Okay, so in our situation, we don't know exactly what are the masses of the planet. What we know is an interval here on which the planetary masses here are. And here it's the line where we are because we know the orbital period of the planet. So we are sure that we are something in this region. Okay. Now, there is a third planet, and this planet is close to mean motion resonance with the 3 to 2 mean motion resonance with the 2 co-orbitals. So this generates resonances, secondary resonances, that corresponds to resonance between the frequency of libration, the frequency of the motion, the relative motion between the 2 planets, which is of order square root of epsilon. And of course, if eta is the average mean motion of the co-orbitals, this quantity is small, of course. So you can have commensurabilities of low order with these 2 quantities. That's what we have. Here, it's another section of the phase space here. It's epsilon, like that. So this line here corresponds to this one, and here that's the mass of the inner planet. Okay, so you can see that you have these gaps here, very unstable in the co-orbital region, but there is still room to have stable motion in the co-orbital region. Okay, so the question is, are there 2 co-orbital planets or not? It's impossible to decide with only TESS observation, so we need more observation, and it's what we have done here. We have obtained photometric observation with these 2 instruments, Speculoos and NGTS in Chile, and also spectroscopic here it's photometric, of course, to look to the transits. And here it's photometric observation to get the radial velocity of the planets. Okay, so the idea is the following. If the planet 1, the one which the period is about 10 days, is in Keplerian motion or close to Keplerian motion, it's easy to compute the ephemerides, and because we assume that the orbit is circular, and then this planet should transit in September 11 and in October 12. So here and there. So here, the observation tells us that, okay, there is a transit, and here, nothing. Oh. And these two instruments tell us the same thing. No transit here, a transit there. So there is a problem. But it's not so sure, because if the planets are co-orbital, there are interactions between these planets, strong interactions. So TTVs, so the transit that do not occur with the same interval between two transits. And here we have two different models here of these TTVs. For example, here you have in red, it's the 10 days planet. And here you see that you can have TTVs of about 2 days for this planet. So between this interval, 1 month, the TTVs can be about 6 hours. So the transit does not occur here, but somewhere here or here. So during the day. So you cannot see this transit. So these observations are still compatible with the co-orbital hypothesis. It's impossible to conclude, but maybe it is the case. So if we reanalyze this reprocess TESS and Espresso, here the radial velocity data, it started to show the possible existence of additional planets, one with a orbital period of 1.9 days, another one 3 to 2 days, and maybe something with this orbital period, 15 days, maybe. Okay, so the idea is the following. If we observe the star during 11 days without interruption, we must see at least one transit of each planet, this one and this one. So this is possible with the new satellite CHEOPS. So it was very difficult to convince the CHEOPS team of the importance of this observation, but as the discovery of the first co-orbital planet would be very, very interesting, it was possible. And then in last August, we have obtained this light curve. So you can see, you can have a model here. It's a model of transit that are fitted to the observation here, and you can see very small dims here, for example, on other large dims. So here, this very small phenomenon corresponds to this planet, so a planet of less than 2 days of orbital period. It's a new one, okay? Another new planet here, these 3 transits here of about 3 days of period. The one that we know, the inner planet observed by TESS here, that transit here and there, and we have just one transit for 2 planets, for the 9 day and the 10 days. So it's impossible. The co-orbital hypothesis is not the right one. Okay, so we have to find something else. So yeah. Oh, okay. If we return, okay, maybe we. Okay. So if the two planets are not co-orbital, the 9 day and the 10 day are not co-orbital bodies, there is no reason to have strong TTVs because the planets are not very close one to another. So no strong interactions and no strong TTVs. So in September here, the 10 days planet should have transit there, and it's not the case. So it's not a planet. Okay, so it's not a planet, and sorry, it's quite long. Okay, one more. Yeah. And then these transits correspond not to the 10 days, but to the 9.96 days. Okay, good. So if we go back to the TESS observations here, of course, we have these 4 transits that correspond to the 6-day planet. Now we know that these 2 corresponds to the 9 days planet, and then we have these 3 transits. Okay, it's not the planet with orbits, with an orbital period of 10 days, that's something else. So the simplest hypothesis is to assign these 2 transits, the first one and the last one here, not to the 10 days planet, but to a 27 orbital period planet. Okay, so we can do it. And then if we assume that the TTVs, the perturbation between the planets are not too large, we can predict the transit of this planet. So it's what we have done, and in September, CHEOPS observed the system, and then, okay, the transit of the 20 days planet was there, and also the transit of this one. Good. So you have an additional planet in the system, not the 10 days, but the 20 days. Okay. And what about this transit? So we have to find something else. Maybe there is a planet, but which one? Okay, so let's summarize. So after reprocessing the data of TESS, Expresso, and so on, and the 2 visits of CHEOPS, we have 4 planets. And it is not difficult to see that these planets are close to mean-motion resonance. So these 2, 1, correspond to the 5 to 3, and so on, and the C and the J are close to the 2 to 1, mean-motion resonance. Okay, but we have much more. Here are the angles, difference of combination of longitudes, mean longitude, that corresponds to these resonances. And of course, these angles vary very slowly because we are close to resonance, to mean-motion resonance, and you can see that for these 3 combinations, the period of variation of this combination are very close to the same value. It's not the case here. So, of course, if we make the difference of this combination, you can have something which is close to 0. This combination of mean-motion between these 2 planets and the combination of the mean-motion between these 3 planets and these 3 ones are close to 0. So the system should be in Laplace resonances. So between these two planets and between these two planets, as the three inner Galilean satellites of Jupiter. Okay. So now, so we have it seems that we have a resonant chain of Laplace resonances, and then in planetary systems, this kind of resonant chain is generated by some physical process. For example, the migration of the planets in the gas disk, because it before it evaporates. So we can assume that, where is the, yes. We can assume that the planet F, this one, which is unknown, but we have one transit of this planet, is a part of the resonance chain. And one very simple solution to put it in resonance is to assume that the planet is in 3-2 resonance with this one, and the planet is in 4-3 resonant with this one. Okay, because these two planets are close to 1-2 in motion resonance, and that gives us a period of about 15 days. Okay, so you assume that you have a period of about 16 days, that you have not too much interaction between the planets, and then you compute the ephemerides, and you observe with CHEOPS. And then, okay, you have the transit here, very close to the predicted time on the transit of the inner planet too. Okay. And now, if you compare all the transits that we have, each of the transits are now assigned to the right planet. So we have 6 planets in the system, at least. We assume that the orbits are circular because we cannot measure the eccentricity of the planets, and then that the system is planar. It's very close to be the case, and then we have the data here of the system. We have very precisely the orbital period, so which gives us the semi-major axis. We know the mass of the star, that's known. With transit, we can measure the orbital, the radius of the planet. So in Earth's radius, so about 1, and here about 3 for these planets. The mass of the planet can be deduced from given density of the planet and using the radial velocities that give strong constraints of the planetary masses, and then we can measure by transit the inclination of the system. So it seems to be very close to the orbit in the same plane. And then, though it's the system, and we have mean motion resonance, we are close to mean motion resonance between these planets. So, as I've shown you before, now we have 6 planets, and if you compute the period associated to this combination, you can see that it is more or less the same thing. So the C to G are embedded in a chain of Laplace resonances. And then you can compute the corresponding angles, combination of these angles. So you have 3 combinations here, and this angle varies slowly around the specific value. We'll see later that these angles are in libration, of course. So we are in this chain of Laplace resonance. Okay, so now a few points about the stability of the system. Here you have the pointer here. You have a stability map, say a very section of phase space here. So it's a numerical integration, a long-term numerical integration. The initial condition are the nominal one, the one given on the previous table. The initial eccentricity are equal to 0, and then vary here only the period, so the semi-major axis of the planet F, and its eccentricity here, initial eccentricity, of course. So here you have we have a stability indicator with this deduced from the method of frequency analysis from Jacques Lascar here. So in red, of course, it's very unstable chaotic motion, and here, when in dark blue, you have stable motion which are very close to quasi-periodic motion. So, okay. So you have islands of stability. The system here, it corresponds to the location of the system, the planet F, here in a stable region, and then you have mean motion resonances here that generate these gaps. And what you see here is that the eccentricities should be small if we want the system to be stable. And if we do the same thing with the other planet, you get the same result. The eccentricities do not exceed a few hundred, not few, hundred. And then we can verify that it is the case if we start with small eccentricities, and if we integrate during very long time the system, the eccentricities will remain very, very small always. Okay. So now another section of the space, of the phase space. This map here, when the initial condition here, where is my, okay, here it's the orbital period of the planet F, here the orbital period of the planet G, the outer one here. The initial condition are the nominal one, the eccentricities are equal to 0, only these two parameters here varies. So here it's the location of the nominal system. So this system here is in this blue island, which is a very stable island. It seems to be the most stable of the map here. And this island here is surrounded by red and green region that corresponds to overlap of mean motion resonances. Of course, you have here this region here, so the horizontal structures corresponds to mean motion with the planet E and J. The vertical, of course, to resonances of high order with the planet E and F, and the diagonal structure, the inclines one, correspond to mean motion resonance between the three consecutive planets, E, F, and J. Okay, and here you have the resonance, the Laplace resonance, where the system is. It's the 2 minus 3 plus 2. Okay, so, and you see that the stability island here is very narrow. If you change the initial condition, the initial period of less than 0.1%, it makes the system strongly unstable. So now these angles. So I've told you before that these angles are in libration. So if you make a numerical simulation with the nominal initial condition, you get this curve. So these three angles oscillate, vibrates around some values here and there. So with period of a few decades here, or a few for this one, and here a few years. Okay, so of course it is not the we cannot predict what is the motion of this angle, because it depends very strongly on the eccentricities of the planets that we don't know. We know that they are small, but we don't know what are their values, and on the masses of the planets. So we cannot know. We are sure that I will see you here. We are sure that these angles are always in libration, but we can know what is the real motion of this angle. So here, in order to have an idea of the extent of the resonant chain versus the mass on the period of the planet F, we draw this plots. So here it's the stability map here, with this initial condition is the initial period of the planet F, and here the mass of the planet F, because the uncertainty on this mass is very large. So here it's the nominal position, and here it's with the same initial condition. The colors here indicate the number of Laplace angle, which are in libration between among these three angles here. So in the central region here, the yellow one on this one, the motion is very stable, and then these three angles are librating. So you are deep inside the resonant chain here. And then we have this ratio between the frequencies, the orbital frequencies of the planets here. And then it seems that it does not depend, the size of this region does not depend very much on the mass of the planet F. But on the contrary, if we change of a very small quantity the orbital period of the planet F, or the semi-major axis, that's equivalent, we fall in this very chaotic region, the red one here, and then if you look at this map, we see that we see nothing. We see that no Laplace angle are in libration. So when you go in this region, when you move a little bit the semi-major axis of the planets, one of the planets, we break this resonant chain, and then we get chaotic motions. And then here, if we are in this region here, so the motion is also very stable. Here you have a lot of blue region, and here you see that you have only one angle that is in libration. Of course, this one, the one that not depends on the planet F. But between the planet D, E, and G, you have another Laplace resonance. So it's in this region that are very stable too. You are also in Laplace resonance, the 2, 4, 6, 12. And this does not depend on the planet F, on this mass, on this semi-major axis in this region, of course. And then you have long-term stability. Okay, so now a few comments. So about the formation, it seems that as long as the system is in the complete resonance chain, the system remains very stable. so on. It's the case if we choose initial condition in the neighborhood of the nominal parameter for the masses, for the semi-major axis or the orbital period. So such a system is very fine-tuned, and it's too fine-tuned to be the result of a chaotic evolution of the system. So this may result from some physical phenomenon like migration on the protoplanetary disk. Okay, that's the first point. The second, here, theoretically, the density of the planet decreases as we move away from the star. So, okay, here you have example, you have the 1, 2, 3, 4, 5, the 5 or the 6 known multiplanetary systems that are in Laplace resonant chain. And if you look at this, for example, here is the density of the planet in Earth density. So here it's the rocky planets like the Earth, the same density. On it corresponds more or less to Neptune or things like that here. So you see that for these 4 systems, sorry, the density decreases here as you go away from the sun. And it's absolutely not the case for TOE 178. And it's very difficult to explain this with the current planetary formation models. It should be due maybe to chaotic phenomenon, giant impact, as you maybe as it was the case in the solar system, or phenomenon of planetary scattering just after the evaporation of the disk. Because if you have migration in the protoplanetary disk, generally it results to a very compact systems, and the gaze damped the eccentricities and so on. So the motion of the planet is very stable. But if the gaze goes away, when it evaporates, there are strong interaction between the planets, and then you can have ejection of planets. So maybe it's the case here, but it's in contradiction with the first argument. So it's a problem that we have to solve. 2 remarks about the inner planet. So the inner planet is close to the resonant chain, but not inside the resonant chain. So maybe it is due to, perhaps it was at the beginning in the resonant chain, just after the evaporation of the gaze, and maybe pulled out by tidal dissipation. We have to see. And about the outer planet, so the last planet is the 20 days planet, J, and maybe there are some planets beyond this one, but it will not be easy to observe this planet because of the small inclination on the line of sight, about 1 or 2 degrees. They will not transit this planet. So the planet G is the last one that can transit. The other one, no. So we only have radial velocities to find this planet. So it's not very easy. But we will see with the upcoming observation, if there is something in the system. Okay, so if you want to know more about this system, you can read these 2 publications here. And thank you.
Okay, thank you.
Thank you.
So we have time for some questions. Nobody.
I have a question. To ask a question in your CHEOPS from 2020, there's some increase in the flux.
Sorry?
In the diagram from the CHEOPS August 4th, 2020, there was some increase in flux. What is the explanation of that?
An increase in flux. So where is an increase in flux? Here? No.
In those.
Yeah.
There's some points where the flux increased quite significantly. What's the explanation for that?
Sorry, it's the next one.
From the observation.
Yes. This. It's the next.
This one, yes.
This one.
Yep.
So no, you want this point? For example?
What is the explanation for that point?
No. I think that there is no explication. That's not realistic. It's a problem of measurement, of observation. You have to look at the average. So, for example, the small dots here, the gray dots are the observation, and the circles are the accumulation of observation during, I think, 30 minutes or something like that. So you have some average here, and even with this average, you have points that are not significant. So no, your average flux is always except here equal to 1. So it's observation. So it's the real life.
So how do we ensure that the points where the flux decreases are real?
Yeah, because it's a statistic. You can you use model here. For example, you have this point, and if it's not real, the model will not converge. So you can use a lot of different models and process all of that, and then you have statistic indicators that tells you if it's the right solution, a good solution or not. So statistically, you can say that yes, it's a transit of a planet.
Is it possible that the star increases in flux and?
No, because we know this kind of star are known, and their evolution of the flux are very constant. So no, and there is many other tests to measure the variation of the flux of the light flux. So now it's it's transit.
Okay, thanks.
I don't know if I convince you, but
yes, you did.
Okay, thank you.
The next one. Well, myself, I have two small questions. First one, the age of this star is known?
Yes, I think so. I don't remember. Maybe it's written in the about 10. It's more than the sun. It's more than 5 billion year. About
more than 5 gigayears.
Yeah. It's known more or less.
The second one.
Yeah.
Go.
The star is smaller than the sun, so maybe the time life is much more than the sun, much more longer.
Yeah, the other question concerns a possible existence of another planet beyond the sixth one. I have read that you have used TTV to compute the masses, okay?
No, not really, no. Because the TTVs are very, very small. So we have to wait for a long time to use the TTVs to constrain the masses. So for the moment, no, it's not possible to do it. So the masses is just due to the radial velocities that we have constrained on the gas and the density of the planet. We know the radius. So we need much more observation to use the TTV that are very small. I think I can maybe show you something if I can. Here we have the the simulation. Of course, it's a simulation of the TTV somewhere. I don't know. I think it's this plot. So yeah. So the TTV are small. It's in minutes here, and it's not more than 30 minutes here. But it's a prediction. We don't. This TTVs varies very, very strongly if the masses are different, and we don't know exactly what are the masses of the planets.
Okay. Well, I have another comment.
Yeah.
I had one question.
Yeah.
But I will not make it because you answered it during the talk. You forgot on the paper to mention the time of integration to construct the stability maps.
Ah, sorry.
Now I have seen the time.
So it's very long. It corresponds to
1 mega year.
Yeah, 1 mega year. Yeah.
Do you intend to publish a paper? It's the complete study of the stability, or not?
Yeah, I think we will try to do it.
Yeah.
But now we have time to do it.
Yeah. Okay.
Thank you.
I hope to know when you have it. It's interesting.
Yeah.
I ask the other people if there are any other questions. Okay. So I thank you, Philippe.
Yeah, thank you.
Thank you very much for this very interesting talk. Okay. The game is over.
Goodbye.
Bye-bye.
So, Marcelo, could you stop to recording?